Good afternoon, everyone, and welcome to today's webinar titled Introduction to the Soil and Water Assessment Tool, known as SWAT. This webinar is sponsored by EPA's Water Quality Modeling Work Group. I am Jason Gilday with EPA, and I'll be moderating today's webinar, and thank you all for joining us today. So a few webinar logistics to start the webinar. First, we hope that everyone has a lot of questions today. The phone lines won't be open, but you can type your questions into the questions box on your control panel and click send. If your control panel is not showing, simply click on the small orange box with the white arrow to expand it. If you have any problems viewing the broadcast, just let us know in the same questions box, and we will post an answer in that box. A phone number is also available on your control panel if you are having trouble hearing audio through your computer speakers. This webinar will be archived for later viewing on EPA's Water Quality Modeling Workgroup page, and we will provide that archive link for you on a slide at the end of the webinar. Also, at the end of today's webinar, you will be able to obtain a certificate of attendance for participating, and we'll provide directions for downloading it at that time. Lastly, the materials in this webinar have been reviewed by EPA staff for technical accuracy. However, the views of the speakers are their own. They do not necessarily reflect those of EPA. Mention of commercial enterprises, products, or publications does not mean that EPA endorses them. Okay, so I think the logistics are out of the way. Now a quick intro here about this webinar series. I'll remind people that this is one part of a webinar series that's been going on. And the purpose of our series is to help water quality professionals to better understand water quality modeling and how models can be used to solve problems facing water quality regulators. Today's webinar is actually the 12th in our webinar series. All of the past webinars have been recorded and archived and posted to our YouTube website. Links to the archive files are available at our Modeling Workgroup website, and you see the link on your page there. And in a few weeks, today's archive will be posted to the same website. And we encourage you, as this is a webinar series, to go back and listen to some of those previous webinars if you haven't already. They do build on one another, starting with modeling basics and kind of up to more of the advanced topics we're talking about today. The audience for this series is, the webinars are targeted at water quality professionals who may want to use or review models as part of their job, but do not necessarily have a modeling background. So as such, we are assuming that you have a basic understanding of water quality science and concepts, but perhaps have limited direct modeling experience. And with that, I'd like to introduce today's speaker. Today's speaker is Dr. Srinivasan, and he goes by Srini. I'm sure many of you have heard of him or know of him. Srini is a Regents Professor in the Biological and Agricultural Engineering Department and also the Ecosystem Science and Management Department at Texas A&M University. And Srini has over 25 years worth of experience in the water quality modeling field and has led watershed modeling efforts to support a number of TMDLs and watershed management and water protection efforts throughout the United States and around the world. So I'm going to hand this off to Srini. Just one last reminder, we'll be asking questions. We'll have question and answer sessions at various points throughout today's presentation. We often get more questions than we can actually answer. We'll do our best to answer as many as we can. I'll be moderating those sessions. I think we have 2 or 3 of them, so please, throughout the presentation, do be typing your questions in as you think of them, and we'll get to them periodically throughout the day. And with that, Srini, I'll let you take it away.
Thank you, Jason. Really appreciate the opportunity here, actually. Good morning, everyone. I'll be presenting a topic on Introduction to the Soil and Water Assessment Tool. I won't be able to do justice of going through every details of the SWAT model in this presentation, but I'll hit the highlights, and then later I'll talk about 1 or 2 applications, one on urban, one on rural watersheds, and then also talk about some large-scale watersheds towards the end, and then talk about where we are heading with the SWAT model development in the future. As Jason mentioned, SWAT It is a model developed jointly by Texas A&M and USDA-ARS. It's a joint project product, but currently it's contributed by many, many more outside of the two groups that I mentioned here actually. So it's truly a global model, the global community model that everybody contributes, and it's an open source, and it's available in our website that I'm going to show you in the next few slides. As Jason mentioned, already we talked about, already there are several webinars that talked about why models and what models can help in analyzing water quality problems and stuff like that. And here I just highlighted some of those key points here actually. So mainly to understand the watershed processes and look at not only the past historical as well as current and the future trend in any of these water quality issues that we may be dealing with. It also helps to identify where are the real pressures or the problem areas or hotspots within the watershed. It can also help to identify what are the impacts of this pressure or how do you mitigate these pressures and how do you respond by various best management practices or conservation practices or alternative scenarios. Then most importantly, the model is not only to predict the past, present, and the future, but it also can inform us, are we measuring the right parameters, or are we measuring at the right location, or are we also doing the enough frequency, for example. So there are lots of ways the models can be put to use to optimize your observation network and monitoring network in addition to the landscape processes and so on. The watershed models in general, they are all in various spatial and temporal scale. As you can see from this slide, the x-axis is actually a spatial scale in meter square. It's not in just meter spatial scale. And the y-axis is in time. So there are lots of different processes that goes all the way from minutes to hours to all the way to day and then annual or monthly scales. So depending on the water quality problem that you'll be facing in, you may need to have your model catered towards any one of these time or spatial scale. A lot of the models are quite capable of handling a lot of the different time scales, but sometimes they lack the spatial scale. So SWAT falls somewhere in day and monthly or annual scale, and we do have hourly scale of certain process, not all the process in the model, especially the hydrology and sediment can be simulated at the hourly process. So this gives you an opportunity to see where each model may fit in. I can easily put each model names in this graph to give a reference on exactly what model may be appropriate at what scale in both space and time. So that leads to the presentation today. This is SWAT. SWAT stands for Soil and Water Assessment Tool, and I have the website listed on the top there actually, and it contains tons and tons of resources, including all the papers, peer review publications published, and the workshops and the conference we organize, as well as the detailed documentations and stuff like that. So I do highly recommend to spend some time on the website to get more information, because I won't be able to cover everything during this short 1 to 2 hour webinar. In general, SWAT is a continuous time step model. You can run the model from few days, weeks, months to all the way to hundreds of years actually. And it's a daily time step model. That's what predominantly used for, but the model is capable of simulating at sub-daily time step also, provided you have the proper weather data to support at a sub-daily time step for hydrology and sediment only at this point. It is a distributed parameter model, meaning not each process in the model is distributed. It is the parameters, meaning the spatial data or the inputs required for the model is spatially distributed, and thereby it can able to preserve the heterogeneity of your watershed in terms of land use, slopes, soils, and so on. It is comprehensive in terms of process, and all the process have interactions, meaning every one of the process simulated in the model has a feedback mechanism, thereby anything that you forget in one place may show up in multiple ways in the model output, thereby you can diagnose the problem to make sure you have the right set of inputs. And most importantly, models are used for simulating alternative management or scenarios. So that's where the real strength of the SWAT is, how comprehensive the model in terms of its processes, but most importantly, how you can simulate the different processes with the different assumptions or different conservation practices to find out what is the ways to improve the watershed, water quality in the watershed and so on. And one of the fundamental philosophy in developing the SWAT model from the day one, both Dr. Jeff Arnold and myself involved in this from the day one, is make sure the model is usable and useful to the end user community, such as the group that we are talking today, and able to use from readily available inputs. Because we don't want to be developing the model with a very complex in nature that's going to be used only by few researchers or few students and few groups that can collect data and apply that model. Actually, that's one of the main reasons a lot of the models do not take off significantly, because of the data requirement is significantly overburden the use of that model. So here we try to keep that in our core principle of what existing data and what's readily available and how to process them. So if you go to our website, you may be able to see it's not only the model, we also provide the data sources for the entire world, whether it's the weather data or land use, soils, whatever that's required to set up a model. So in a nutshell, one should be able to set up a model anywhere in the world with SWAT using the data sets that we provide. I'm not saying they are the best data out there. Obviously, there are better data sources, more local data sources that could be supplemented, that could be improved on. But the main thing here is to make sure the model is going to be useful and usable only if there is data to go along with that, actually. So that's the prime principle of providing not only the model, but also the associated databases to set up model anywhere in the world. So, as I said, there are several processes involved in the model, and I know this slide is very busy. I'm not going to go through every one of them, but in a nutshell, SWAT handles both atmospheric loads, such as your wet and dry deposition of nutrients like nitrogen and phosphorus, for example, and also takes into account all the soil processes, whether all the way from infiltration to runoff to lateral flow and groundwater contributions and soil management like organic carbon and things like that. Then, of course, climate is the main driver. So we use all the climate variables to simulate the plant interactions. And the most important of all is the land management. How does a particular landscape is managed and how they are simulated to represent the real watershed processes. So we provide lots and lots of different processes and outputs. I'm going to go through them in the next few slides. I just want to give you the big picture on what SWAT is capable of doing. So one of the processes is the landscape process, actually. That's where the main core strength of the SWAT model is, the landscape processes. So like this picture shows, you can take a landscape, and that could be divided into sub-watersheds, actually. So it could be divided, in this case, could be 3 subbasins. This could be one subbasin, this could be another subbasin, and the third subbasin may be what you see on the right-hand side of the figure. So that subbasin may have sub-watershed or subbasin, they're all the same. So that sub-watershed or subbasin may have different land uses. It could have forest land, it could have a rangeland or agricultural land, or cities, urbans, wetlands, and so on and so forth, actually. So, and they also could be distributed across various soils, and they may be in various slope classes or various slope positions. So SWAT with a GIS interface takes all those information coming from a GIS and overlays all the GIS layers to come up with a unique response unit, the hydrological response unit called HRU, which is a combination of your subbasin map, land use map, soils map, and a slope map. So that becomes the basic building block to set up SWAT model actually. So every process is computed at the HRU, the hydrological response unit that you see here. Okay. Now more recently we have added a landscape process where you can divide your landscape into a floodplain that are close to the river and a hill slope, and then the divide, the watershed divide actually. And the next slide I will show you more detail here, for example. So you could have a watershed divide and then a hill slope and a floodplain. So the HRUs within the watershed divide could interact both surface and subsurface to a hill slope HRUs, and that can interact with the floodplain HRUs before that moves into the river for the river transport from upstream to downstream. So this is kind of a little bit compromised. We still have a lot of aggregation going on between HRUs at each of this unit level, meaning the divider, the hill slope, or the floodplain level. Okay. One of the other major strengths of the SWAT model is you can configure or you can set up your model in many ways actually. I'm just showing you the spatial discretization here. Later I'm going to show you about how you can set up different processes and develop model. In other words, you can just use the same data sets and you may be able to even come up with about 20 different configurations of the SWAT model because of simply the number of processes and the spatial configuration. On the left-hand side, you can see this could be just one soil, one land use, and one slope, all lumped together actually. A very quick and easy calculation to simulate what's happening on the landscape. Or you can talk about more traditional way of doing it as a HRU, where you overlay the 4 GIS layers, the soils, land use, slope, and subbasin map. Or you can do the landscape positions like the one I showed you in the previous slide, where the yellow regions are the divide areas, and the orange are the hill slope, and the red area are the floodplains, for example. So all the HRUs within that could be simulated separately, and then they interact accordingly, both surface and subsurface level. Or the last one is the gridded version actually. So you can decide to divide the model, say 1 hectare or 1 square kilometer or whatever the size that you want based on the size of your basin. You can divide that, and within each grid then act as a subbasin. There you can have multiple hydrological response units depending on your size. Sometimes if you're doing 1 acre plot or 1 hectare plot, you may just want to do 1 HRU per hectare. Or you could have 10 kilometer by 10 kilometer or 5 kilometer by 5 kilometer, and you can have multiple HRUs within that. So all these things are all possible with the same inputs actually. The input doesn't change, it's the configuration or how you want to set up your model is going to change. So what are some of the upland process we do on the landscape by HRU? So obviously weather is our driving factor. You need at the minimum the temperature, maximum temperature and rainfall as a minimum input. If you have wind speed, solar radiation, relative humidity, we can take advantage of that actually. You can either use point rain gauges or aerially weighted rain gauges like PRISM data set, or you can use NextRad, Doppler radar. So there are lots of ways you can bring in your information. Then of course hydrology is a major driving factor that drives your sediment, plant growth, nutrient cycling, nitrogen and phosphorus, pesticide, land management, and of course bacteria. Bacteria is the least amount of testing is done in this model. It is added around 2005 or 2006, and there is only very few projects were done with the bacteria compared to any of the other processes that are well tested and well refined or well evaluated by various users of the model actually. One of the other reasons the SWAT is being successful is not many water quality model or hydrology model have plant component as a central core. So in SWAT, plant is a central core basis for modeling actually. If anything is not functioning right, it will show up in either in your sedimentation or nutrient, all will become out of balance if your plant is not growing properly. For example, if you put a grass type that is supposed to be summer grass on a winter time, the grass may not grow. Actually, if the grass is not growing, that means you have more sediment and more nutrients may be available for the rainfall runoff process. So any mistakes or anything that you do on the plant growth will show up in everything, all other process. In other words, plant growth component is what's keeping all the process intact or exchange information back and forth actually. So plant component is very important in SWAT. And in this slide just shows you some of the rural or agricultural watershed management, whether that is riparian management next to the rivers, like you see here are buffer managements, or it could be contours or bunds or some kind of a stone terraces and whatnot, or it could be the animal management that you see on the lower side, the bottom two slides or bottom two figures. Then you can have an agricultural chemicals that could be pesticides, nitrogen, phosphorus, whether you apply them directly on the surface or you knife in under the surface or below the ground, or the kind of tillage practices or multiple cropping, different cropping, contour cropping. So there are lots of things that you can simulate the various real-world practical management practices in SWAT. So the limit is going to be how much data you are going to be able to obtain to represent your landscapes. So that's what is going to most of the time limits how detailed will be too detailed or how detailed can we afford to collect data. So this one figure shows you in a nutshell what the hydrological balance that SWAT simulates actually. So you take a HRU that could be represented by a tree crop, or it could be a grassland, or it could be a cropland, or it could be a range or city or whatever it may be, and you have a that is going on a soil. That soil could be divided into up to 10 soil layer called root zone, and then you have an unsaturated or wedo zone that follows right behind that is going to be a shallow aquifer. So like you see here, this is the shallow aquifer part. Shallow aquifers are typically between, say, 2 meters to 10 meters or so. Then you have a confined layer and a deep aquifer. So when there is a rainfall, that rainfall is first divided into runoff and infiltration. So for runoff, we have two sets of processes. Either you can use the NRCS curve number approach or green and amped approach, either spatially explicit manner or more little bit of lumped manner. Then once the water reaches the infiltration, it's going to get distributed across your root zone, and any excess soil moisture will return as a lateral flow. If you have tiles is one of the major components that is incorporated in SWAT, where you can introduce tiles anywhere along the root zone to have any of this water get intercepted, and then tiles will flow directly to the river also actually. So you can model tile management in SWAT. Then once the water reaches below the root zone, and that gets traveled to the shallow aquifer, and that water has become available either as a return flow or a base flow back to the river, or discharge into the deep aquifer, and the water that's in deep aquifer sometimes interact with the river back again, or some of the water could go back as a capillary retention back to the soil surface. Okay. SWAT handles only up to shallow aquifer. We do not keep track of water that goes into the deep aquifer. So if you really want to know more about your deep aquifer processes and you need to have a true groundwater model simulation, SWAT has been successfully linked with another model, public domain model, USGS model called ModFlow. And we have an interface and we have all the tools and technologies available to take any SWAT model and link that with USGS model ModFlow in SWAT website, so you can read more about it and download the tools and documentation about it. I'm not able to go through every one of those stuff. Actually, I'm going to hit only the nitrogen as one of the key examples here, but you can talk about phosphorus or pesticides or any other process, including the plant processes. So in a nitrogen, we keep track of 4 forms of nitrogen. One is the organic nitrogen, then ammonia, nitrite, and nitrate. So some of the inputs to the process is in this landscape. This brown area is your soils. Then you have the anaerobic condition, meaning soil water. Then of course air. So the input for the nitrogen could come in from atmospheric nitrogen or chemical fertilizer, or it could be manures or sludge or animal waste and so on. And once you input all those, and then of course the plant itself, if you have some kind of legume crops like soybean or any other legume type of crops, alfalfa, they can also incorporate nitrogen directly into the soil. So all those things are taken into account in the model, and once that's inputted, the model will simulate every day the transformation of the different processes of immobilization or mineralization and denitrification process, and it simulates the various sources. The plant can uptake only in the form of nitrate. However, some of the nitrate can also leach to the groundwater, or under anaerobic condition through denitrification process, the nitrate and nitrite can exit as a nitrogen oxide or nitrogen as a gas, which is a greenhouse gas. And when you harvest your crop, the harvested crop is going to also carry a lot of nitrogen and phosphorus with them actually. So what are some of the losses? The losses are going to be leached to the groundwater, the net gain or loss from inside the soil, nutrient balance, and of course, most importantly, your runoff and sediment that from that HRU to the nearest river or nearest to the channel process that's going to take over at that point actually. You will get every one of these output that you see here. Actually, the only input is either your fertilizer, atmospheric nitrogen, or manure, are the only three inputs that you have to provide. If you don't provide them, the model will also estimate that actually, and then the rest are all model outputs. Every one of these detailed outputs you can get from the model. On the channel process, SWAT can handle both point and non-point sources. So the non-point source pollution that we talked about so far is the nutrients or the pesticides or the sediment and bacteria and so on that's coming from the landscape processes. Once that reaches the river, then any point source, either the municipal, industrial, or wastewater discharge plants that may directly discharge into the river, both gets integrated, and then the channel process takes place. SWAT channel process is only a one-dimensional steady state model called Qual2E. So Qual2E is what is incorporated, which is an EPA public domain model, is what's incorporated in SWAT, and it takes into account only along the longitudinal direction of the river or the flow. It does not take into account anything what's happening across the river or in depth. It's not a three-dimensional model. It's a one-dimensional model along the river actually. And there are other models such as WASP, C=W2, and several other hydrodynamic models have been successfully linked with SWAT, and various papers and publications have been done to link the landscape process to the river process if you really need much more higher level of higher sophistication of your channel process, for example. SWAT also has been linked to other index-based model. One of the index-based model is Aquatox, which is a model developed by the EPA, and it is interfaced with SWAT. So the output from the SWAT will become an input to look at things like the fish abundance or fish survival or fish tolerance and things like that actually. So there are other indicator models have been used to take the SWAT output and be able to simulate the river processes. Okay, I know it's a long list. Actually, I'm not expecting to go through every one of these inputs and outputs. Just to these presentations, and the video will be available for you to go through more leisurely. But mainly, we need soils, land use, precipitation, and climate. Sorry, the climate, precipitation, land use, and topography. These are the first 5 are the key inputs that's required for the SWAT interface. The rest are all optional, depending on some watersheds, you may have a lot of best management practices or ponds and reservoirs or land management and so on, and including point source and atmospheric depositions. But the minimum requirement to set up your model is the first 5 input is all you need in a GIS form. These are on the right-hand side. It shows you all the different outputs that you can get. All the outputs you can get either at 3 spatial scale, either at the HRU level, that means the individual field or farm level, or a parcel level. You can also get at the sub-basin level, which is a group of HRUs belongs to that particular sub-basin. And then you can also get the river process actually. Anywhere along the river, any point along the river, you can get model output. So some of the output that you can get is what's shown on the right-hand side. So these are all the different variables, all the way from stream flow to sediment to nitrogen, the 4 forms of nitrogen and 2 forms of phosphorus, pesticides, BODs, algae, dissolved oxygen, bacteria, and metals. So here it's giving you the output. You can get the output at 3 temporal scales, not only 3 spatial scales, but also you can get 3 temporal scales, daily, monthly, and annual average. So here is all the blue colors that shows you that outputs that you can get on hydrology, such as evapotranspiration, soil water runoff, infiltration, and so on. And then sediment is the water quality sediment yield from the landscape, but also sedimentation in the river process. Then, of course, nutrient losses both at the landscape and the river process, pesticides. Then, of course, the crop or the biological output, like the biomass, crop leaf area index, soil fertility, and so on and so forth, actually. So it's an extremely detailed model. So as I was mentioning to you, there are ways in where you can spatially construct your model, like lumped model or HRU model or a landscape model or a grid model. You can also take each of those spatial models into further process-based models. Actually, here you have options to choose different potential evapotranspiration based on the input of your data. If you have all the weather variables, you can use Penman-Monteith. If you have only temperature, you may want to use only Hargrave model, for example. So you can have sub-models within the SWAT model for the various process and the interactions. Same thing for runoff. You can use the NRCS curve number method or green and amped method. For channel flow, we have 2 different equations, one for variable storage coefficient or Mushkingham-Kunch method. On water quality, you can either turn off water quality or turn on, meaning you can turn on or off your Qual2E model that's built in within SWAT. You're not running a Qual2E model separately, it's already embedded in SWAT. All the equations and the process are all already embedded in SWAT. We also provide lots of tools and technologies to make the user life a lot simpler. You can use either ArcGIS interface or QGIS. QGIS is a public domain GIS system. We call ArcSWAT and QSWAT. And we also provide a calibration, uncertainty, and sensitivity tool called SWAT CUP. CUP stands for Calibration Uncertainty Program. And then we also, for visualization, we have a VisSWAT where you can visualize both spatial and temporal and animations and all kinds of things you can do, including calibrations and stuff like that, actually. And we do publish very, very detailed manuals that is in both in English as well as several other languages, including recently somebody has done in Vietnamese and so on. And then, of course, SWAT has been a well-established model. The very first model was published in 1992. Since around 2003, it's much more stable, and several newer version was released, but it's not every year or every few months. It's once in few years, actually. So it's pretty stable. And later part of the presentation, I'm going to talk about the next generation of the SWAT that's we are working on, we are developing, that will come up in the next year or two. I just want to hit the highlight on where we are heading with SWAT. Okay, so the major, to wrap up on the SWAT theory or SWAT conceptual part, the major strength of the SWAT model is the upland process, where we have a comprehensive hydrological water budget or water balance using physically based inputs and where plant growth such as crop rotations and crop yields and biomass are the main central core component of the SWAT, with nutrient cycling in the soil and in the river process, as well as the land management like what I listed here. There are almost, you can imagine any ag land, rural land management, including grazing, can be incorporated in the model. On the channel process, we have a very flexible way of configuring your watershed, all the way from a grid to landscape to HRU, all the way to a lumped model actually. You can have water diversions, water transfers, import, export of water from other basins to a current basin, or from the current basin to other outside the basins. You can model sediment deposition and scouring at the same time. We have 4 different sediment equations in the model that you can choose for channel process. Then you have nutrient and pesticide transport, as well as modeling very detailed pond, wetland, and reservoir impacts could be modeled with SWAT. SWAT cannot do everything, obviously. It has got limitations too, such as lake water quality is not one of the major strengths of the SWAT model. If lake is part of a bigger watershed that you're studying, you can use SWAT, but if lake is the end product that you want to study for a TMDL, then you may want to think about bringing in other much more sophisticated model like WASP, which is another EPA public domain model, or C=W2, which is a US Army Corps of Engineers model. So you can use any one of those 2 models for lake water quality. They are also already successfully linked with SWAT outputs. Currently, only the sediment and hydrology can be simulated at the sub-daily time step, and you can have the urban conservation practices are somewhat limited. It's still more and more is getting added as we speak, and I'll talk about one of the applications later in the slides. Okay, I'm now transitioning from the SWAT as a model to an application where how the SWAT was used for a TMDL or develop a watershed protection plan, what we call watershed protection plan in Texas. Okay, so this is a project that was done in North Central Texas, okay, where we are trying to assess the best way, the cost-effective way to evaluate the various BMPs to reduce the phosphorus level in a watershed, Cedar Creek watershed. You can learn more about this watershed protection plan on from this website. Okay, just to give you a background, the lakes, as you see here, there are 5 lakes that supply water to about 2 million people in Dallas and Fort Worth area. Okay, and TRWD is the operator of the reservoirs. They have the rights to the reservoirs water to supply that water to they are the freshwater supplier to the about 2 million people. That's going to get expanded to about 4 million in the next 10 years actually. So water is key in Texas, a valuable commodity in Texas. So we are developing a watershed protection plan for the 3 lakes, the Eagle Mountain, the Cedar Creek, and the Richland Chambers. So today I'm going to talk about an example of the Cedar Creek, which is the watershed that you're seeing here on the right-hand side of the Trinity River that flows through Fort Worth and Dallas. Okay. One of the major concerns for this lake is the increase in chlorophyll. So we all know the nutrification or the eutrophication of the lake is one of the major causes for increase in chlorophyll content. So here we are showing you the trend, annual trend of chlorophyll in the lake. So this is what's in the lake. APR is not the lone APR. Actually, this is the APR annual production rate of about 4%. So every year there is an increase of about 4% of the lake chlorophyll. So this is one of the major concerns. So the TRWD, they came to us and we are working with them extensively in developing this watershed protection plan. So obviously the framework here is the ultimate goal is to study the lake itself. So we did include the WASP model here for the reservoir, and we use the most current GIS data, and we also did an extensive wastewater treatment plants in the watershed. And of course, SWAT is the major landscape model or the watershed pollution model. and SWAT linked inside the SWAT is got a water quality for the in-stream process. Then for the lake, we are using the WASP model, and all these things are all happening with the stakeholder input actually. So as an essential step in the watershed protection plan, stakeholder will be involved in every step of this process in order for their approval and agreement before any of this process get underway actually. Then we also included an economic analysis of choosing what is the best management practices to produce in order for your watershed model. Okay, then finally develop the watershed protection plan. Just to give you a background, in the interest of the time, I did not put all the detailed statistical distributions of land uses and things like that. The cropland and the urban landscapes in the watershed is about 6% each. But the 6% of the land is producing almost 35% of your nitrogen production in the watershed. And the 6% of your urban watershed is producing about 12% actually. And the rangeland, which is almost about 60 to 70% of the watershed, produces about 50% of the load actually. So those are the major three players that if you are going to control the nutrients going into the lake. But this lake is not limited by nitrogen. It is limited, it is caused because of the phosphorus, not because of the nitrogen. Okay. So this is the, after all the calibration validations and developing the model, this is based on a 37 years since the lake was established. This is the average annual load going into the lake actually, how much of sediments and nitrogen and total phosphorus going into the lake. So based on the WASP data analysis, if you want to change the trend in the chlorophyll in the lake, one have to reduce the phosphorus by 35% in the watershed loading in order to do that. This is based on the stakeholder analysis as well as the lake model. So this is our target, is to reduce the total phosphorus amount by 35%. Okay, so there are many different ways to achieve this 35% reduction goal. So with the help of the stakeholders, we come up with a list of different best management practices as you see on this list, like filter strips, grade stabilization structures, grass waterways, terraces, conversion of cropland to pasture land, and prescribed grazing. On the right-hand side, we are just showing you a few of the ways how you can model in SWAT. Okay, so if we assume that 100% of this land is going to be adapting this eligible land that's going to adapting these practices, what will be the impact of phosphorus reduction? So if everybody put a 15-meter width of buffer around the farm land, that will help to reduce only about 30% of the phosphorus, for example. Or if you put a grade stabilization structures, it may be able to help to reduce only 2.3%. So we come up with the list of possible reduction to the different strategies under 100% adaptation, and then gave all this information to an economist to run through an optimization model to figure out what is, because we also did a survey on the stakeholders about what is acceptable, how many people are willing to adapt that, and then at what rate and things like that. So all those went into the economic model, which I'm not presenting here actually, into making a decision on what exactly is we can implement. So we selected 7 BNPs after the economic analysis, and where you can apply up to 50% of the filter strips, 100% of the grade stabilization structures, and critical pasture and planting will be about 20%. Terraces will be about 15% adaptation rate, and the wastewater treatment will be up to 100% adaptation rate, as well as prescribed grazing about 15%, and then aiming for a total reduction of 35%. So we took all this information and then we ran the model actually, and this is the baseline. When you look at the baseline, this is the total amount of phosphorus coming from the landscape. So what you're seeing is a sub-basin map, and these colors schemes that you see on the left-hand side, legend goes from green mean lower and red means higher. There are so many kilograms per hectare. They are comparable to pounds per acre, if you want to keep this number in mind actually. And this color does not change. So first we run the SWAT model, then we do the phosphorus loading by sub-basin, then we do the ranking, and then finally apply the BMP on the selected ranked watershed. Then we go back again. So this is the iterative process that went on in developing the model. So what you see here on the left-hand side is again the same figure I showed you before. Here is where the load coming from the landscape, and this is how it reaches the lake actually. So this is the channel process I'm showing you on the right-hand side. Okay, so this is the baseline. So after we implemented the filter strip 50% of the landscape, this is the example of filter strips. So you can see the change. So this was the baseline, and here is after implementing the filter strips. This is where the reduction strategies of phosphorus in various subbasins. Next, we incorporated some of the grade stabilization structures, and then able to again put grass waterways, for example. So every one of them is starting to show you some improvements in the various practices that could be incorporated or implemented, like terraces, wastewater treatment plant, and conversion to pasture land, and prescribed grazing. And there are 2 different kinds of prescribed grazing, and finally, 2,000 feet buffer around the lake so that no immediate contribution from the lake itself actually, or the surrounding areas within the lake. So with that, we were able to achieve a 35% reduction in the lake that's able to sustain on the long term actually. So let me stop right here and maybe allow to have more questions. I'll let Jason take over at this point.
Yeah, thanks, Srini. And I'm just going to pause for a minute here and let people get some more questions typed in. We've got a number of good ones so far. Just a reminder to folks to keep typing your questions in as you think of them. I'm sitting here kind of organizing and shuffling them around, and I'll start asking Srini in a minute. Just a quick technical note, there's been a number of people that have reported having some sound problems. And my recommendation would be if you're having trouble with your sound from your speakers on your computer, there is also a phone number that should be showing up on the audio portion of your GoToWebinar screen, and you could call into that phone number. The sound on the phone tends to be a little more clear than the sound on the computer. But I think overall, Srini, you're coming through loud and clear for most people, so it doesn't seem to be a systemic problem. But with that, I'll just start asking a few questions, and we've got some good ones. First of all, we got a question on channels and maybe losing reaches, and even reaches that go that kind of disappear and reappear downstream. Can SWAT deal with kind of losing reaches, and how does it do such a thing?
Okay, yes, SWAT can handle it. Actually, you can also handle as a closed basin, or closed basin meaning where the water goes and disappears and then maybe appearing downstream farther from the distance there actually. So if you know those type of knowledge actually, and a lot of USDA studies have provided that kind of information, so you can make that as a spring, as an input, where it reappears actually. Wherever it disappears, you can model that actually, and you can stop the modeling and then start the modeling again downstream somewhere where it reappears. Either it can be in one model setup, you can do that, or you could be as 2 separate model actually. One may be model up to the closed basin, and then there may be another one at the downstream one, depending on whatever the thing. We have done that in several watersheds in Texas, especially in San Antonio region.
Excellent, thanks. A question about BMPs. I think SWAT has a number of kind of BMP structures and functions kind of built in, at least that's what I'm understanding. And the question is, you know, does SWAT allow you to input some innovative BMPs, maybe something that's not the norm, and how would that be done?
Oh, excellent question actually. In fact, yes, we do. We have what we call generic BMPs. Let's say, for example, there is a practice, but we don't know exactly how it's implemented. All the process is not really, you don't care about it or you don't know about it, and it can't be simulated very quickly. You can come back and say, okay, based on our engineering design or based on our things, we may be able to reduce sediment by 30%. So if you say on this particular HRU, I'm going to implement that. So whatever the sediment that's generated from that HRU, we reduce it by 30% and only the rest will go to the river, and then the river process will take over. So there is generic best management practices reduction coefficient that you can input directly into the model at the HRE level or at the reach level or a subbasin level that will take care of whatever the reduction strategies that you are trying to implement so that you can quickly do an analysis to see. So a lot of the time people will want to do a reverse. Let's say they know the target. They say, how much should I reduce it in order for me to able to meet the water quality standard? So they can use this type of generic BMPs to put a strategy there and then try to go back and figure out what are the best way to achieve that.
Thanks, Srini. Another question, and I think you're going to get to this in a minute, but I'll ask it anyways. It looks like SWAT might have some, perhaps some limited application in urban environments. Can you give us a quick preview on what you're going to talk about with SWAT or in the urban environment?
Yeah, thank you, Jason. We have been working very hard with several cities, especially the city of Austin, on developing several specific modules for city or urban environment, urban development, urban growth, and urban management, and things like that, actually. So we have added a lot of new modules which may or may not be available to you today. There are some of them are already available. There are more things coming up. So I'm going to make a presentation about some of the soft BMPs and hard BMPs on urban environment and how that might help in a urban TMDL or urban settings. So I'm going to talk about that in the next few slides.
Yep. Srini, there's a number of questions about linking models together. So I'm just going to kind of lump and summarize the questions. Can you give us a quick summary of how you might go about linking SWAT to something like WASP or CE Qual W2? Just kind of a broad overview of how that kind of thing is done.
Okay. So if you talk about a hydrodynamic water quality model like CE Qual W2 or WASP, you can do it at two levels, either at the riverine level, meaning hydrodynamic level along the river process. That means you take the SWAT output at the subbasin, edge of the subbasin, and dump that at various entry point along the river where the WASP will be simulating or CE Qual to be simulating the river process itself. That's one way of doing it. Either you can do that on a daily or monthly or whatever the temporal scale those models can accept, actually. The other way of doing it would be on the lake. So you can let the model simulate everything, including the river process, until the lake, and then the lake model, such as, again, WASP and CE Qual W2, because they are both hydrodynamic model and also a lake water quality model. So depending on how you want to interface, you can hand over your handshake from SWAT to these other models before the riverine process or after the riverine process or the channel process until it gets to the lake, actually. Same thing with the mod flow. So we have set up the mod flow to run either at a daily model. SWAT could be running on a daily time step. Your mod flow model could be running on a monthly or annual time step. So it all depends on how you are spatially discretizing your watersheds and how far you need to delineate your watershed to capture your aquifer process and things like that. I can tell you that we have more than about 30 to 40 publications already published on linking SWAT with other models. I just talked about only 2 or 3 models, but there are many other models have been linked successfully with SWAT, and they have been using that in various contexts. And in the SWAT website, we provide all the literature's references for all the 3,000 publications we have done so far with SWAT.
Thanks, Srini. We'll get through a few more, and I know we have a lot of material, so maybe we'll save a few of these questions for later. But right now, you mentioned Qual 2, I think it was Qual 2E being available within SWAT right now. And could you maybe talk about the Qual model a little bit and what the difference is between Qual 2E and I think the latest version of is Qual 2K something or another? And are there plans to update it, or are they different?
Okay, yes, there are some differences, especially on the sediment, because Qual 2E does not take care of sediment process with nutrients, actually, whereas in SWAT, we do take care of that. So in a way, it's not 100% of the call to E is what's in SWAT. We have modified the call to E and incorporated when we incorporated in SWAT. On call to K, there are some subtle differences, but most of them are parameters driven actually, because a lot of SWAT's call to E model has got constant parameters like, for example, the clarity of the water or the light penetrations and things like that. So a lot of those parameters are different in call to K versus call to E actually. So some of them can be adjusted, but there are some process differences that needs to be, that is not in call to E, is in call to K. So if users are interested in that, we can certainly work with them. And if they want to develop it, we'll be more than happy to support them and whatnot. But yes, there are some differences between call to E and call to K.
Thanks. Kind of similar then, I guess. Does SWAT simulate channel bank processes, bank erosion, and things like that, and may perhaps the associated nutrients that might come with that?
Yes. So on the bank processes, actually, we have recently meaning as of 2014 or 15, we added about 4 different channel erosion equations actually. So all the way from completely eroded channel to a channel that is still forming or still happening actually. So we have 4 different processes. So you can choose different equation for different sub-basin reaches. In other words, you don't have to choose just one equation for the entire watershed. So if you are in way upland where you have a lot of gully erosions and a lot of sheet and rill erosions, you'll be able to choose a particular equation for that actually. As you go more established channel downstream, you may be able to choose another equation that's suitable there. So if you know there is a lot of channel process, there are a lot of bank erosion and slushing and things like that going on, you may be able to choose equation appropriately when you're modeling the system. And along with the channel process, you are also going to have the nutrients along with the sediment that goes with that actually.
Okay, maybe we'll do one more question now and save the rest for a little later. The sub-daily flow options in SWAT, and actually there were a number of questions on time series in SWAT. Can you describe that a little more, time series in SWAT in general? What happens at sub-daily, what happens at daily or monthly? One specific question is, does it accept sub-daily rainfall as an input and produce, and what does it produce with that?
Okay, excellent question. SWAT runs only at 2 time steps actually, either sub-daily time step or daily time step. These monthly and annual are simply aggregation, both spatial and temporal aggregation of your output generated either at the sub-daily time step or at the daily time step, and then give you the output at the monthly and annual. SWAT will never run on a monthly or annual, always it runs on a daily, if not sub-daily. On a sub-daily time step, you have to have sub-daily rainfall or breakpoint rainfall. So once you input the breakpoint rainfall for every minute or every hour, depending on how you want, every 5 minutes you want to give the input, you can provide them. Then the model will simulate for that time step the hydrological process and the sediment process. Your evapotranspiration and the soil process, all those stuff may be done still on a daily time step actually. They are all distributed based on various hydrograph fittings actually, whether it's a triangle or exponential form and things of that different natures actually one can choose from. But only the hydrology and sediment are simulated at the sub-daily time step using sub-daily rainfall input. All the other processes are still daily, such as your evapotranspiration, your channel process will be also sub-daily for sub-daily rainfall input. The nutrients and things like that, what's happening, how the plant grows, all those things will be on a daily time step.
Thanks, Srini, and thanks everyone for your questions. I know there's probably 50 or 100 questions I haven't gotten to here, but we have a lot more material to cover. There will be a couple more question and answer sessions, and please keep typing them in, and we'll get to them the best we can. We'll save some time at the end, hopefully a big chunk of time to get through the majority of these. And with that, Srini, why don't you just keep going? Okay,
thank you, Jason. Thanks for those good questions. Actually, please, as Jason suggested, please keep piling them on. So next, I want to talk about a little bit about an urban modeling application that we did with the city of Austin. Roger Glick is the city engineer, and Lila Goslick also assisting Roger. So here, what we did is we evaluated the various city ordinance or city guidelines on new land development. So Austin is growing very fast. I think it's one of the second or third most growing city in the U.S. right now. And so they were trying to look at how does this change in hydrology and sediment of different development regulations using the sub-daily SWAT model actually. So like as I mentioned, we have implemented various BMPs and options to run on urban environment actually. So some of them are using sub-daily model. You can have sub-hourly simulations, which includes overland flow, stream flow, ponds, reservoirs, point sources, also the soil erosion and sediment transportation processes. Some of the urban BMPs we have implemented a sedimentation or filtration basin, retention or irrigation basin, detention pond, and wet ponds. These are all the hard BMPs, meaning structural BMPs. Then there is lots of green infrastructures like green roofs, rain garden, cistern, as well as porous pavement. So these are all some of the soft BMPs also have been incorporated. This is not released to the public yet. This is still under evaluation by the city of Austin. So once that's done and we have good enough justification for model simulating reasonably well, this will become the next release also actually. So currently the urban structural BMPs are all in SWAT that you can use them if you are using the model as it exists in our website. Okay, so this is the watershed, okay, that the city wanted to evaluate under various scenarios or various ordinance that city has put in over a period of time. So as you can see, it's completely undeveloped. There may be a small pond in the upper part of the watersheds here actually, agricultural pond, but otherwise it's pretty much undeveloped area. So we run various different scenarios. One is the undevelopment scenario. Another one is the pre-waterways ordinance scenario that was existed before 1974, okay, where there is no control, there is no rules at all. Then there is a waterway ordinance scenario that was established between 1974 to 1986, where you can do only detention, okay, and then wider easements. And then a comprehensive watershed ordinance was passed around 1986 that exists until today, okay. So where they're talking about some retention and detention ponds as well as some of the buffers around the rivers. Then finally, there is a new ordinance that is getting proposed in the future actually, so that is also evaluated. So these are all the, when you see the UND or pre-ordinance and WO, these are all what they mean in the subsequent slides actually. So again, this is the original landscape, okay, mostly open land, grasslands and rangeland and so on. So that's why you don't see any of the other colors. So as you go through them, we have simulated various different configuration, like for example, what happens if you put a commercial or or industrial or residential landscapes actually. You can see it's kind of a regular pattern. We didn't predict exactly where things are going to go because there's not even roads to know where exactly all these things are going to go. But you can see the creek. So this is pre-ordinance before 1974. And then with the 1974, you have some wider main canal or main creek protection. And with the current ordinance between 1986 to now, that's widened significantly actually. And this is where the future. It's not only the prime main river, but it's also the tributary all the way to the subdivisions or all the way to the back of individual houses maybe need to be protected actually. So we evaluated all these 5 different scenarios, and the results I'm trying to show you is based on that at a hourly time stop simulation. The model had a rainfall input of every 5 minutes in this analysis. City of Austin is collecting data in an extremely detailed manner actually. And we also then several scenarios of how the urbanized area, such as the irrigation and the fertilization of lawns, and how do we protect the channels because we are going to have more buffers, and then of course how much of this the land is going to be developed both for residential, commercial land with full employment of all the different BMPs, and then one large detention ponds in the middle of the basin, which is reach number 9 or subbasin number 9. So as you can see in this slide, the flow rate, which is cubic meter per second, has, when it is pre-development, before 1974, you can see it could get as much as 45 meter cube per second. The axis here is in hour actually, so it's, each one is an hour, and the rainfall is in millimeter on the right-hand side axis. So there is a huge difference, almost 40% difference in the peak flow between the fully protected land versus pre-development, for example. Okay. Or if you want to look at this more of a return interval or a flow duration curve kind of thing, actually, you can see between undeveloped, which is this green, and fully developed with all the best BMP you can put in, which is this dark blue actually, and this red is the pre-development actually. So that's what you're talking about, and the cyan is the current ordinance here. So again, you can see there is a huge differences depending on whether you're looking at a 5-year return interval versus 25-year return interval, how much is the peak flow. Because 3 things they're looking at. One is the peak flow, sediment, and wildlife. Or so this is the impact on erosion potential. Like you can look at the reach number 20, which is almost close to the watershed outlet. This is where the width of the river currently, due to the erosion, with or without the development, it can expand as much as 100%. Okay, so that's what it's showing here. This is in percentage actually. And here we talk about the aquatic life. So again, with the implementation of the BMPs, you are able to extend the low flows all the way to almost 90 to 95% of the year because of all the various measures that you can put on the landscape to reduce and slow down the peak velocities and have more water in the river more time than even at the pre-development. Right now you can see only 50% of the time that creek is flowing when there is a rain actually. The remaining 50% is not even flowing actually. So there are ways in which you can evaluate the various BMPs and develop your own ordinance and then help work with the land developers to make sure some of these can be met so that we don't need to worry about all the issues that may bring about the development in an urban environment. So in concluding this urbanized study, actually, the development prior to the regulations had a negative impact on flooding, erosion, and aquatic life potential. And the detention designed for large rainfall alone cannot help here actually. So they can reduce some of the peak flows, but they alone cannot going to solve the problem. So the flood detention, that's what I'm mentioning here, flood detention alone will not address the issues of erosion and aquatic life. And the Austin regulations, since the current water ordinance actually implementation have been beneficial with respect to flooding, erosion, and aquatic life, and more are planned in the coming years actually by working with the stakeholder, which is the land developers, on how to improve that even further actually. So they were using the models as a way to communicate to the stakeholders as well as involve the participation of the developers to agree on certain standards and procedures and protocols to develop the framework for urban development. With that, I'm going to transition to some national applications. Okay. For example, one of the major applications that was been going on for some time is called SEEP. SEEP is, stands for Conservation Effects Assessment Program, led by USDA and RCS, and there are other partners involved in it, including USDA-ARS, of course, Texas A&M, and several universities participated in that, as well as like TNC, for example. So they were all included in the development of the national assessment. It is a national assessment. It was authorized around 2002 through Farm Bill, where almost 40-fold in increase on land conservation program budget has increased. So I think the Congress wanted to know how much are we getting in return for the increase in spending on conservation measures. And the current SEEP is using 8-digit watersheds. Those of you who are familiar with the watershed, say I think there is 2-digit watershed, which is a river basin, then 4, 6, 8. There are about 2,000 of them, 2,100 of them in the U.S., the lower 48 states. So SWAT is the main watershed model that simulated all the non-agricultural landscapes on the river process, whereas there is another sister model called APEX that simulated the cultivated land. Okay, so we combined the APEX output inside SWAT, and then SWAT simulated all the non-cultivated landscapes, and then the process, including the point sources and everything, the river process done by SWAT. I won't be able to do justice to talk about SEEP by just one slide here actually. So for more details, these web links are quite useful. They have extensive reports on wildlife SEEP or range SEEP or cropland SEEPs and things like this all over the U.S. So I'm going to just present a few slides from the SEEP output or SEEP reports for Upper Mississippi. Okay, so this is the Upper Mississippi River Basin. As you can see, the states, Minnesota, Wisconsin, Iowa, and Illinois, Missouri. And the bar graph that you're seeing here is the model developed or calibrated model developed output of if you did not have any practices on the ground. That's what this red bar, all those red bars actually. Each block is equal to 2.5 million tons of sediment. Okay, so the green are the current practices, current conditions, meaning including all the BMPs that we have implemented by the USDA and NRCS, because NRCS did an extensive survey to collect such data and input into this process. And then I would say more like a brownish or dark red is the one where if you remove all the cropland and put back pre-humane condition actually, where there's no settlement and nothing, what would happen to the sediment actually? So this just to give you the lower and upper bound. So if you did not incorporate anything, that's this red bar. And if you don't have any cropland at all in the watershed, that's this dark brown. And the green is where it stands right now after the BMP is implemented by the NRCS. So this gives you an example of how the model was used to characterize the impact of the government programs in helping farmers to reduce their contribution that going into the Gulf of Mexico, for example. And here is a nitrogen. The one I showed you the previous slide is for sediment, and this is for nitrogen. And again, you can see them. In the nitrogen, we have a few more scenarios. Not only the current condition, that's the green. Okay, here each block is about 100 million pounds. Okay, that's how much nitrogen is coming. And the blue is treated, only the critical area, only targeted area, critical area get treated. The red is for all lands that can be treatable, was treated. Then the like a gray color, which is enhanced nutrient management, meaning adding soil phosphorus index or adding, allowing the farmers to input only if there is enough fertilizer based on the soil testing and things of that nature. Then, but that's only on highly vulnerable areas. And the last one, the dark brown, is adding the nutrient management for all eligible land within that watershed. So that gives you the range of reduction that one could expect from the current condition to all the way to the extreme of protecting the landscapes and protecting the management, land management, and so on and so forth at the outlet of Upper Mississippi River here actually. Okay, so the Missouri comes and joins here later, and the Ohio will come and join also below this region. So this slide shows you the entire Mississippi River Basin. That includes the Missouri, the Ohio, Ohio and Tennessee, Upper Mississippi, Lower Mississippi, and the Arkansas River. All put together, how much of nitrogen that's leaving the landscape, meaning at the HRU level, how much is a load coming from the landscape to the river, and how much of that thing that's loaded to the river is reaching the watershed outlet, is what you're seeing. The right-hand side is what's delivered to the Gulf of Mexico, and the left-hand side is what is detached from the landscape to the nearest river, actually. So if somebody wants to target some programs and things like that, at least this gives them an idea of where are some of the highly hotspot areas that one may want to focus on, actually. So the level of details can go all the way from an individual HRUs in an individual watershed to all the way to a river basin scale at looking at the Gulf of Mexico, for example. That's the SEEP that was going on for nearly about 10 years, actually. But more recently, what we call SEEP2, meaning the next generation of the SEEP2 is moving away from the 8-digit to a 12-digit simulation, actually. Already we have experimented that in several places, especially Lake Erie with the help of TNC, and upper Mississippi River Basin, also the Ohio and Tennessee River Basin. OTB means Ohio Tennessee River Basin. And there are several papers already being published where we selected a 12-digit as our watershed and simulated all the different processes, including things like biofuel and the impact of converting lands to the biofuel plants like switchgrass or miscanthus and things like that, and look at their impact on sediment and stream flow, and also look at the grain yield and the plant biomass and stover removal. If you start removing stover to feed to the biofuel ethanol, how that's going to impact the nutrient cycling in the landscape and so on and so forth. So a lot of improvements have done and a lot of papers have been published, and this in SEEP2 we may be going in the direction of modeling the entire U.S. at a 12-digit basis. So with that, let me stop and maybe answer a few more questions on either national or urban-related modeling we talked about.
Yeah, thanks, Srini. Again, encourage people to keep typing your questions in. I'm going to actually broadly answer a few questions right now. We've got a number of questions so far on calibration. In other words, how do you do it? What do I do? And things like that. And instead of asking Srini about that, I'm going to refer folks to some of our previous webinars, specifically webinars 1 through 3. We're all about setting up and calibrating models, and then a few of our other webinars cover that in a little more depth. And because we're a little pressed for time today, and because those other webinars are archived on our website, I'm just going to refer folks to those if you have more questions about just general model calibration and setup. Also, there's been a number of questions about getting data. In other words, where do I go get my land use data? Where do I get precipitation data? And same answer for that one. We've covered a lot of that in some of our previous webinars. And again, just refer for folks to go check those out. And I think a lot of your questions would be answered after that. And then lastly, we've got a lot of questions, Srini, kind of on the specifics and the ins and outs of some of the examples you presented. You know, folks are asking, why did you do this and why did you do that? And I've kind of purposely skipped over a few of those, and that I'm hoping that the intent of today's webinar is to give folks kind of a broad introduction to SWAT and how it can be used. And the intent wasn't really to get into the specifics of a specific project. So I'd encourage folks to follow up with Srini or some of the other project partners if you have kind of more specific questions on the various example projects that Srini has presented, because I think we could burn up a lot of time getting into some of the specifics of how and why you did various models for various basins. So my apologies if I don't get to your questions on those specifically, but we still do have a number of general questions that I'm going to get to, Srini, so frankly we probably have another 50 of them. So I'm just going to get going. This is kind of going back to the beginning and catching up here. You mentioned that, you know, the one-dimensional feature of Qual2E was a a limitation in SWAT. Could you maybe just provide the audience with a quick rationale on why you think that is and maybe what could be done?
Okay. So because we are looking at only on the longitudinal direction along the river, what's happening, what transformations and what changes and what biological activities and chemical reactions and things like that, we are not simulating what may be happening vertically in either in depth or on the width actually. So that means there are lots of processes that may be happening like settlement sometimes or changes in sediment oxygen demand, for example, in the river and stuff like that. They are not thoroughly tested because we are looking at along the length and we are looking at a steady state, meaning for the entire reach, it's going to be assuming it's a constant for a given time step, which is daily means daily, hourly means hourly, and whatnot. So those assumptions sometimes is not valid. Let's say, for example, dissolved oxygen, because we know dissolved oxygen changes every minute by minute, for example, or every stretch of the river and things like that actually. So because we are not able to discretize it, because both spatially and temporally, sometimes those outputs only able to best represent an average condition, not what may happen on a very peak flow or what may happening on a very low flow, for example. So three-dimensional model like the hydrodynamic model like WASP and C=W2, they do take care of that actually. But not all problems require that kind of detailed modeling, because as you get into more detailed modeling, you also need detailed input out of channel geometry and channel dimensions and channel slopes and roughness coefficients and things of that nature. Not everyone will have such a detailed input to every watershed that you want to model actually, especially if you're talking about like Mississippi River basin level and things like that. Maybe at a micro level we can go and collect the data and able to input that, but at a relatively larger size watershed, practically resource-wise is going to be a demanding task actually. So that's the main reason why some of the simpler approach is good enough for most of the applications, but some may demand these larger ones or more detailed ones also.
Thanks, Srini. In the example you were just talking about, you mentioned kind of the APEX model or APEX approach. Could you give us a little more detail about what that is and when folks might want to use that?
Okay, very good question. APEX is like I said, is a sister model, meaning SWAT, APEX, and there is another model called EPIC. They are all same family of models. They all interchange code. They are all interchange the process at the point level or at the field level actually. So they all have the same process. At the HRE level, APEX, SWAT, EPIC, they are all very similar. But APEX has got a lot more detailed process of connecting the fields. Like you can connect one field to another field and you're able to simulate at the micro catchment level. Let's say if you have about, I don't know, 5 square mile or 10 square mile watershed and you know every detail of everything what's happening in that watershed, then you can use something like APEX. But as soon as you start to go to in the hundreds or thousands of square mile watershed area, then APEX may not be able to handle that just because of the assumptions that made in the routing and things like that or in the processes is limited to only for the small watersheds or small area. But APEX has got a lot more BMPs than SWAT. You can physically represent, like for example, if you have a lagoons or if you have a animal management like a CAFO operation, confined animal feeding operation, you can simulate that entire operation within APEX, whereas in SWAT is just a representation of that animal management actually, because within the watershed you may have 10 different kinds of things actually. We represent that with 1 or 2 of that typical operations, whereas in APEX you can place exactly where the operation is happening, how the land is treated, how the land management may be simulated. All those things can be done in APEX. So it has got a lot of strength and it's got some limitations. The limitations are going to be the size. One other thing is going to be the size of the watershed that you can apply for.
Thanks, Srini. We have a number of questions on BMPs. One, are you planning to add BMPs for reservoirs like alum treatments or sediment removal? Or is that already in SWAT?
No, they are not in SWAT. That's a very good question. I mean, that could be done actually. And I can see how you can do the sediment removal, but alum treatment, like I said, the water quality component of the SWAT is somewhat limited. So I think that may fall in. If you're going to really study the reservoir, we may recommend looking at a WASP or CUCOL-W2. So hopefully they will be able to handle that particular part of that actually.
Thanks. A question about sediment. Does SWAT have the ability to model sediment aggradation and degradation within a river reach?
Yes. So SWAT uses what we call stream power theory. So we look at the critical velocity, and in the same day or the same reach, one day it could be depositing, and another day it could be eroding actually the channels. But we do keep track of the balance, sediment balances actually. So that means what eroded yesterday may get deposited in the next reach or within the same reach, and that get pushed on the following day. So the deposition and scouring are simulated, and we have a sediment balance for each reach by reach on everyday basis to keep track of where the sediment goes.
Thanks. A question about, early on you were talking about a gridded approach to HRUs. Could you expand a little more on that and how SWAT deals with that?
Okay. So let's say, for example, if you want to take your watershed and overlay a grid on top of that, and we are developing GIS tools to automate this whole procedure, so the next release of the interface will be able to delineate your watershed on a gridded basin, so that every grid has to have a channel process, because SWAT, the subbasin and channel process are intertwined. So in other words, you cannot have a grid or a subbasin without a channel. So you have to have a channel. So at least you want to set up your size of your grid in such a way it can have at least some kind of concentrated pathways of water and sediment and nutrients moving through the system. So once you define that actually, then you will be able to simulate, just like the subbasin process, you can have multiple HRUs, or you can have single HRUs, or you can have a limited number of HRUs. So you can be able to choose how you want to represent that grid on the landscape side and also the river process. Sometimes the whole grid could be only a river process, for example. So there are only any landscape process at all. So it all depends on how they are connected together and how wide and how big is your grid. So depending on that, you may be able to set up your model accordingly. And the grid is mainly meant, or at least a lot of people are using it so that they can link it with other models like groundwater models, for example. So ModFlow is also runs on a gridded approach so that you can have a mesh link between ModFlow and SWAT. Or sometimes people are bringing in data from atmospheric or climate change models and things like that, so they want to simulate each grid point of a climate downscale climate model as the grid for SWAT model also. So sometimes these were necessitated because of the other reasons, not because of the watershed process reasons.
Great. Maybe sort of similar. How is the loading potential for different land use types defined in the model? In other words, you know, what loads come off of forest, or what loads come off of agriculture, or is it the question is it an event mean concentration or buildup and wash off, or can you explain a little more how that works?
Okay, excellent question. And no, there is no built-in wash-off coefficient for any of our land uses actually. Everything is simulated based on the land process, especially the soil and the soil erodibility and the slopes, and then of course the rainfall runoff process, and the most importantly the plant. Okay, so if you have a plant and you forget to apply fertilizer and the plant did not grow, that means the whole land is available for erosion, and thereby there is no vegetation that's covering the landscape. That means your potential goes through the roof and you get more runoff, more sediment, more of everything. But at the same time, if the land is covered with the vegetation, you are going to have the leaf area that's going to covering the landscape, thereby the impact of the rain droplets onto the ground is going to be minimal, thereby you are not going to have the same amount of erosion or same amount of runoff and things of that nature actually. The only place where we are using built-up and wash-off equations in the model is for urban landscapes. That's only for the built-up area, not because in the urban landscape is divided into two classes. One is the open landscapes or pervious region and an impervious region. For the impervious region, we have a built-up and wash-off equation as well as the process equation. Actually, the user can choose which equation they want to simulate, and those came from the USGA's National Water Quality Assessment Study, where they had an even mean concentration values that is part of the database in SWAT. So the user can either choose that option for only for the urban built-up area contribution of nutrients or sediment and so on. For the rest of them, they are all simulated based on the land management, the crop modules, as well as the rainfall runoff process.
Thanks a lot, Srini, and thanks again to everyone for typing in questions. Please keep typing. I know we have 10 or 15 more slides to get through, and we're running a little short on time. So, Srini, I'll hand it back to you, and then we'll do one last Q&A session at the end.
Thank you. Thank you. So there are two more topics I want to cover. One is project that's funded by USDA Office of Water called HAWKS. So HAWKS stands for Hydrological and Water Quality System, where we are developing the SWAT model for the entire U.S. at 3 spatial scales, and you can get output also 3 temporal scales. So I'm going to talk about that, and then finally I'll come and talk about quickly about the future of where we are heading with SWAT, like what we call SWAT Plus. Okay. So what is HAWKS? HAWKS is a National Hydrology and Water Quality Assessment System. It's got generated based on our past national projects that was funded by USDA, and it's mainly to support the national, regional, and local applications. Okay. So as I mentioned, there are the 8-digit watershed in the U.S. There are about 2,100 of them, whereas at the 10-digit level, it's about 15,500. At a 12-digit, it's almost 83,000. Okay. So that's, if you take that watershed, and within each of that watershed, this is how many hydrological response units, which is the combination of your subbasin, land use, soil, and slope. Okay. Each HRU is roughly about 5.8 square mile in the 8-digit model, whereas at the 10-digit model, it's about 2.5 square mile. At the 12-digit level, it's just 1 square mile, actually. 1 square mile means 2.56 square kilometer. So that's how many hydrological response units are available. So everything is pre-processed. All the inputs and all the data that you require to run SWAT anywhere in the U.S. is already pre-processed and ready to go, so that in about 5 minutes or less, you will be able to run the model anywhere in the U.S. Okay. So here is an example of a Dallas County of 8 digits. So this blue line is an 8 digit. So the 8 digit is basically the size of a county. Okay. And this is the same area. This is a 12 digit. 12 digit is on the average of about 50 to 70 square mile, actually. So that's the size of a 12 digit watershed. Okay. So this gives you, the HAWKS gives you a visually, it's all web-based system, it's a cloud-based system, so you come in and say, okay, I want to model a watershed, you zoom in to any area or like a Google Earth engine type of thing, you can come and select an outlet, it automatically shows you what are the boundaries of your watershed, you can choose, you want to run at an 8-digit level or a 10-digit level or a 12-digit level, then it automatically brings all the inputs required for that area of the watershed that you selected, and including all the weather input and everything, and set up your model in about 5 minutes. Then you can start running scenarios, like you can run climate change scenario or weather scenarios or change in climate sensitivity or change in land use or change in point sources. Anything that you want to do, you can quickly run the model within a few minutes actually, and you're able to start looking. So this gives you an example of climate change scenario. For example, you can choose which climate change model, which scenario, which time period you want to run, and what kind of scenario, like A1B or RCP 2.5, 2.6, 4.5, or 8.5, and things like that. And here are the simulations. These are the models that's available currently, the various climate change models input data sets are already available within the Hawk system. So the applications of the Hawks are mainly meant for land management or crop management or conservation practices, or you can look at the pollution control like either non-point source or point source or atmospheric deposition and so on, as well as climate change applications that you can do at anywhere in the U.S. at any the 3 spatial scale, 8, 10, or 12-digit watersheds. It's using all the public domain databases, and it's got a very nice way of looking at graphs and charts and maps and so on. No GIS software knowledge or inputs required. It's all web-based architecture. All you need is your iPhone or maybe a tablet or a laptop with a good enough internet connection. And it significantly reduces one of the analysis able to show it reduces your time to put together a model, first version of the model, about 90%. Okay, 90% reduction in time to set up a model. Okay, so overall, SWAT has been applied in various large simulation systems at the national scope, such as the humus, SEEP, and various TMDL at the local level analysis. A lot of them are ongoing. And then, of course, there are several regional or national climate change and water quality assessment is done with the SWAT. And then, of course, Hawks is the most recent one that's getting developed, and it is available for anyone to use. If you just type in Hawks, you'll be able to get to our website, and you can sign up. It's free to use at this point, courtesy of US EPA. So with that, I'm going to transition my last segment of my presentation, which is where we are heading actually. What is next in SWAT? So we are going to call that as SWAT Plus. I think that's how much we are creative on our naming systems. So SWAT Plus is a completely restructured version of the SWAT model. It's going to make your sharing of different model components or even linking to ModFlow and everything is going to become a lot more easier and simpler, including WASP and things like that, because we're structuring such a way it's all extremely module and data-driven model actually. So so link to other models and adding new process, everything will become very, very simple. Okay. So also these are all our spatial objects now. So we have a reservoir object, channel object, aquifers, HRU plant soil relationship, and all this can be connected. So I can connect directly a HRU to a reservoir, a HRU to a channel, or a HRU to an aquifer. So anything can be linked to anything. So previously it's a lot more structured. Now it's not going to be. So the user will have, if you want to think about a piece of the puzzles, you can put together your own watershed puzzles and how you want to set up your own model actually. So previously I talked about the spatial configurations and the sub-models within SWAT. Now you have even much more flexibility in way in which you want to link the various components of the SWAT model to the various other components actually. And it's going to be available in a public domain again through a version control system called Bitbucket. So the current system, we have one file for each data for each object. Now that's all going to be consolidated actually. So previously, if you're going to set up a file system for the upper Mississippi Basin, you may have a close to about 500,000 to 1 million input files. Now we are going to consolidate all of them to 30 to 40 files. So the maximum number of input files one has to generate is between 30 and 40, rather than the millions of files that used to get generated in the past or in the current SWAT version. And it's going to develop our input-output process in the model, and it's going to reduce our runtime, and it's going to be easy to manage and maintain, and you will have an opportunity to directly read and write to a database. And we are also making all our interfaces completely public domain so that you don't need to have an Excel or access to run our system actually. So thereby both domestic and international users could be able to benefit from the process. Okay, so this is the current configuration on the SWAT, where you have a watershed that's divided into subbasin, and the subbasin is divided into HRUs. The new SWAT plus structure is going to be a watershed, subbasin. Then we are going to separate out all the water areas. They are going to be treated differently. Then all the subbasin could have what we call landscape. Okay, this is the land position or hydrotopes, and then within, like we talked about, the ridge, the hill slope, and the floodplains, and so on, and they can control their own HRUs within that actually. So there's one more level of delineation and separation of water areas, which is, we think, very key for the future of the model development. I'm not going to go through read all of them actually. In general, it's going to give you more flexibility in terms of how things are connected actually. So if, for example, if the HRU that are in the divide area, the watershed divide area is directly linked to another HRU or another downstream, you can connect them directly actually. So you don't have to go through the channel process to get connected to from one place to another place. So that could be a overland connection, subbasin connection, and aquifer connections actually. All those can be customized heavily in the new system that we are developing. And then there's going to be a lot more opportunity to do the land processes actually. Previously, we used to do a lot of deterministic manner. Now it's going to be more on rule-based manner actually. That means you can develop your own rule when to trigger certain things. For example, if you want to apply a pesticide and you say there is a recommendation you should not apply pesticide if there is going to be a rain, or if the soil moisture is X or the wind speed is Y, you can develop your own rule and make that as a management input. The model will not apply the pesticide in those days when it is not meeting a particular condition, for example. So there are lots and lots of ways you can trigger different rule systems to trigger different processes in the model rather than saying what happened on a particular day or so as a model input. So there are lots of flexibility going forward in how to do that actually. The aquifers and reservoirs are going to have their own module. They are not anymore linked to HRUs or subbasins. So you could have an aquifer that spans across multiple watersheds or multiple subbasins. Your reservoirs could be on multiple subbasins also actually. So you do not, current limitation is they all have to be within one subbasin. You no longer have that limitation that actually. And that helps you to easily link to other models like pot flow. Okay. And the spatial connectivity, which I already alluded, actually, it's very going to be very flexible. Sometimes it will be over confusing for normal users, actually, if they are not sure how to connect them. So we will guide them through the GIS interface on how to connect all the spatial objects, but user will have opportunity to overrule that or connect it any way they want to, actually. So in concluding, model has been used very extensively. I have not touched any of my international applications with SWAT, and it's been well tested all around the world, and it's been extensively used, and it's a product in development for more than 50 years from within in USDA. Currently, we have more than 2,950 peer-reviewed publications were written in the model development applications and use around the world. It's truly a world community model. It's no longer just a Texas A&M or USDA-ARS model because the contribution is truly from the community of the SWAT users, SWAT developers all around the world. And it is a public domain, and it's made available to anyone, open source and public domain, and all the information is available on our website. It's one of the most widely used water quality and water supply, climate change and land use change model. One of the recent publications that I saw, the number of papers, they reviewed all the different kinds of models. SWAT stand the #1 model in the world in terms of the number of peer-reviewed publications as well as the number of applications and so on and so forth. The very next model had only about 120 papers actually. So that's a difference between where the SWAT is today versus where the rest of the models in the research community. With that, let me stop right there and maybe answer more questions.
Thanks, Srini. Appreciate it. We've got a few questions on Hawks and SWAT Plus that I'll get to in a second. Encourage folks to keep typing things in as we go through here. We do have, let me see, about another 15 minutes available for question and answers. And I'll maybe say a few things while people are finishing getting their questions in. The Hawks model, there has been a national EPA webinar on that already, although it wasn't archived. We're hoping to have another more in-depth kind of like this, a 2-hour webinar on hawks. So stay tuned for that, and I can advertise that through the list of people that I have through these modeling webinars. There are a number of interesting features in that. It's got some unique applications if people are interested in that. So I encourage you to stay tuned. And yeah, with that, let's just get going on some questions. Srini, right off the bat, when will the SWAT Plus model be available?
The SWAT Plus, the hydrology, the sediment, and the crop growth modules are all completed. So those who may be interested want to do a preliminary beta testers, we are already working with several of them actually. So if there are interests, they can certainly contact me or Jeff. We'll definitely want to start working with them actually. The official, or what I call is release of this module will be later this summer in our next SWAT conference in Poland. We'll be announcing this and releasing it with a GIS interface. The first GIS interface will be on QGIS, and later we will release an ArcGIS interface maybe later in the year actually. But it will be extremely rough or maybe preliminary, so there is a lot of things still need to work, a lot of testing need to be done. So we are always looking for great volunteers, graduate students. Thank you.
With SWAT Plus, can you maybe explain a little more how it's going to be integrated with GIS and some of the NHD geo databases and data layers and things like that?
Okay. So currently, again, because SWAT Plus or SWAT itself, the SWAT families are the generic model, we are not tying to any specific databases or data structure, but we will make what I call plugins where it will make your life simpler to bring any data sets. For example, if you have a climate change data set or NHD Plus or other stuff, we'll make your life simpler to easily import that data like CDL or NLCD on the land use or StatsCo or Sargo, things like that. Anything that is a standardized, published, well-established databases, either federal government or state government databases, we can ingest them directly into the model through the GIS interface. But we may not tie that to any specific, because we also have a lot of international users who may not have access to or who may not be having the format or the specific thing. So you can build the model from scratch, or you can bring in well-established data sources directly and able to use that with SWAT and SWAT Plus. So that's the direction we are going, and you will be able to do grid-based modeling, landscape-based modeling, things like hydrotopes, HRUs, and sub-basin delineations. So you'll have a lot more flexibility, and how do you connect all of them? Actually, you can even connect between HRUs, one HRU to another HRUs on landscape and things like that.
Thanks, Srini. I'm going to pause for 1 second and advance a slide just so that we get the contact information up. Again, I know we're not going to be able to get to all the questions folks have. We've had several hundred today. It's great. It's been a really engaged audience. I love it. And I encourage folks to email myself, Jason Gilday, or Srini. Our emails are on the screen here if you have some follow-up questions, particularly the ones about the specifics of some of the examples that Srini presented. So some more questions, Srini. With hawks, can you go ahead and change or update land use or other inputs, or is it kind of a static or fixed model?
Okay, you can change. I mean, already we provide you 3 different weather data sources. For example, we give you the NCDC, the National Climatic Data Center, the NOAA National Weather Service data set. We also provide the PRISM data set, the gridded data set, and NextRad. So we are providing 3 different weather input that you can choose from. You can also choose the current land use. Then you will be also able to input your own land use change actually. Let's say, for example, you have done some analysis for your watershed, and you know this is land use X is going to change it to Y at this percentage on this day of the year or this time period. You will be able to input that in the model. You can simply input that as an Excel sheet, and then we take that information and then run the model based on current land use until the day you say it's going to change. Then you can change the input. Same thing on point source. We run the model with the point source. Whatever we have, you can download that point source. You can update your own, because the point source data, what we have is a national database, but you may have much more refined or better input at the local source. You can update the point source. You can update your atmospheric deposition, for example, or climate variability. Any of this stuff that can be updatable, we give them the tools to supplement that. Actually, after the base model is set up, you can supplement that and then refine it and run the model. One of the other beauty that I forgot to mention in Hawks is, even though it is a completely operational on a web-based system, it gives you the power to download the entire thing onto your local hard drive, and then you have 100% customizable way to model the watershed actually. So then you have the full power, because we also provide you a desktop tool to run any number of iterations, any number of scenarios, any number of fine-tuning that you want to do to your input to represent your watershed actually. So it's the beauty of both having an online versus offline system.
Thanks, Srini. I think that's about it that we have right now for the Hawks and SWAT Plus questions. So I'm going to just get back to general SWAT questions that have kind of piled up in my questions box here over the past couple hours, if that's okay.
Sure.
SWAT and bluff erosion, could you explain how you would go about dealing with that in SWAT? And in particular, thinking about the Mississippi River example you presented, I'm guessing there's a lot of bluff erosion that goes on there, maybe what you did with that.
Okay, so we looked at some of the reports from the USGS actually, where they showed various places where the things getting channelized, or where the levees and things of that nature actually. So we were able to incorporate a well-established channel versus channels that are still forming, and able to find out where some of the bank erosion or gully erosion. That's one of the things that we are adding a significant improvement in SWAT Plus is gully erosion. Those erosion that may be happening in the first or second order streams that may be contributing significant amount of erosion to the main channel and whatnot actually. So we have incorporated some of those things, and that's a special version of the model that was used for the SEEP analysis. And because remember, the landscape itself was simulated by the apex, it's only the channel process, and the non-agricultural land area is what was simulated by the SWAT. And as I mentioned, in the SWAT we have 4 different equations that can able to handle a well-established channel to all the way to an infancy of channel that's still forming. So you can choose the appropriate equation, and then of course calibration. We had to calibrate throughout the stretch of the river at various locations using some of the USGS data to make sure the model is producing reasonable results.
Thanks, Srini. I'm going to go ahead and advance a couple slides here again so people can have a look at this. We talked about there is a participation certificate and available for today. It's the link on your screen here, but you don't have to write it down. Everyone that registered for this webinar and attended will be getting an email tomorrow with a link to the certificate, a link to our TMDL modeling website that you see on the bottom of the screen that has all of our archives and our contact information. So if you'd like to write it down so you could look at these things now, I'll leave this up for a few minutes while we're getting through a few more questions. I think we've got about 5 minutes left. Yeah. Okay, Srini, when modeling BMPs in SWAT, is there a certain order in which you should go about doing things? In other words, should you look at maybe, fencing first and buffer strip second, or can you just do anything at any time?
I mean, you can, as a modeling system, you can do anything anytime, but there are things why you should do one before other actually in order for you to see the multiple benefit or the cumulative benefit actually. So there are logical progression one has to follow in order to get the most bang for the buck actually. So you don't want to have a sedimentation pond built when you go and do an on-site management that's going to reduce the sedimentation significantly, thereby your sedimentation pond become obsolete at that point actually. So yes, there is a way in which you want to go in a more progressive or a more systematic manner to accomplish your goals rather than just doing all at once, actually.
Yep, agreed. CAFOs in SWAT, is there a module for that or anything? Can it be used to do CAFOs, or would you maybe rather use something like Apex? Could you explain that a little bit?
Okay. The CAFOs at a larger scale can be modeled in SWAT, but if you want a very, very detailed, for example, you have an animal, confined animal operations, then that's going to have all the waste products is coming to a lagoon, and then the lagoon slurries is taken out and automatically in a sprinkler system is going to spread on a landscape. So if you want to model every step of that process, then I would say Apex would be the better tool for that actually. But in SWAT, you can say, hey, this subbasin has got a CAFO and it produces X amount of manure. Then you can say it's get applied on these HRUs. Then you can represent the lagoon system or the CAFO system in SWAT, but it may not need to go through the exact process of how they are all the dots are connected, because as I said, SWAT is more of a watershed process. It may not be able to represent every detailed land process and able to track how they are connected or how they are linked to each other and things like that actually. So it's a scale question. So if you're really dealing with the CAFOs and if your watershed is very, very small, then I would say Apex would be a better tool there actually.
Okay, maybe I think we got time for one last question, and then I'll do a quick wrap up. You mentioned that SWAT really is kind of a multinational or kind of applicable at the world scale now, and there's a question about, do you find that SWAT is more applicable in some parts of the world and not others? And the asker is specifically asking about rural Africa, but I think maybe could you comment, is this model better for just agricultural areas? Is it better in the arid west versus the east coast? Is it better in one country versus another?
No, that's, I think the model, we have modeled the entire Africa continent for that matter. The model is not limited. It is our data that's what is going to limit you where you can apply or where you cannot apply. Even though we provide the data for the whole world, the resolution of the data may or may not be applicable to a watershed that may be only, say, 100 square mile in a rural Africa or in Asia or any other place for that matter, actually, because your rainfall, for example, may not be represented at that local level. But if your rainfall is only half a degree by half a degree, 50 kilometer by 50 kilometer, that means if your watershed is much smaller than that, then obviously your rainfall variability or the temporal variability may not be able to capture by the model with that publicly available databases. You need to have local data. As far as applicability, I don't see there is any reason why this cannot be used or where they have not been used. And so far, it's been used successfully. That's one of the reasons why this publication rate is going through the roof, is because on an average, we are publishing about 450 peer-reviewed publication every year, actually. And that's more than one a day is getting published. And we have more than 500 different journals is publishing, peer-reviewed journals are publishing our work, actually. So it's widely and well accepted, but I could admit to say that not every component of the SWAT model is tested everywhere. The most extensively tested is the U.S. in terms of water quantity and water quality. Most of the other, like in Africa and other places, is mainly used for land use change, climate change, and hydrology. Not many projects is done with water quality. If there is a water quality, it's most likely sediment only, not nitrogen, phosphorus, or pesticide, anything like that. So that may be still to be explored or still to be evaluated in those modules of water quality in many other places in the world, actually.
Great. I just advanced one more slide for everyone that's still with us. We are still looking to have more of these modeling webinars. At the end of the presentation today, in a second, there'll be a survey that comes up, and we do look at those survey results and use them to guide where to go next with our modeling webinars, whether that's you'd like to hear more about specific models or applied usage of models. So please take some time to fill that out. This webinar will be posted to our website that you see on the screen now, hopefully within a month or two. It takes a little time to get things processed, so please check back on that. And Srini wanted to give you a huge thank you. This has been a great presentation. I really appreciate it. And you can tell by the number of people online here with us and the number of questions that this is a topic that people are interested in. And encourage people to contact Srini or I if you have more questions. Also give Srini a little plug here. He does offer a number of in-depth SWAT training sessions throughout the year. I believe some at Texas A&M and some in other parts of the country or world. So check on their website for that. And with that, we'll end the webinar. Thank you, everyone, for attending.
Thank you very much, Jason. I really appreciate the EPA put in the efforts in setting up these type of educational webinars, and I truly enjoyed it, and thank you for everybody for participation.
Okay, bye, everyone.